So what if I asked you to find a probability of rolling a sum of 4? Okay, so let's list the ways, or think about the ways that that could happen. So the first one is orange, right? What if I rolled a 1 on the orange? What would I be able to get a sum of 4? Yes, if I rolled a 3, okay. What if I rolled a 2 and a 2? Okay. Now we don't count that twice because you can't, you know what I'm saying? You can't distinguish the difference. What about if I did a 3 on the first die? Then a 1. Okay. Are there any other ways that I could get a sum of 4? No. How many ways did it happen? 3. The total possible outcomes are 36. So the probability would be 3 out of 36, or 1/12. Okay, so that's a really, really simplified version of how probability works. Sometimes it can get really complicated when you're figuring out certain types of hands and cards, right? Because some of those were tricky when we were doing that the other day with combinations and stuff. So in general, let's do the formula for probability today. The probability, I'm going to abbreviate, of an event. The shorthand that we write that is P of E equals the number, that's the number sign, not the hashtag, the number of possible outcomes of the event divided by the number of outcomes in the sample space. Do you know what that phrase sample space means? Have you heard that before? Yeah. The sample space, let's put a box around it so if you don't know. The sample space is all of the outcomes in an experiment. In other words, if I would go through, and actually they might have done that. If you flip to the next page, do they list all of the possible outcomes for 2 die later on in the page or not? Down at the bottom. So if I would actually go through, we found out how many there were 36. But if I would actually list them out, 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 2 1, you know, if I would list every single thing of those out, that's called the sample space. If I count up how many of those things are, that's what goes on the bottom of my fraction. Okay, can probability equal 0? It actually can. It cannot be less than 0. If the probability of something is 0, what does that mean? There's no chance that it's going to happen. And for instance, let's say in this case I said, hey, what's the probability you roll a sum of 30? Can't. The probability of that would be 0. There's also a probability of 1. Probability is 1 when something is going to happen. 100%. Okay? So if I said, what's the probability you're going to roll 2 dice and get a sum that's an integer? They're all integers, so that's going to happen. So probabilities have to be greater than or equal to 0 and less than or equal to 1. If you found all of the possibilities in a sample space, the sum of all those probabilities to be valid should equal 1. Okay, so the sum of all probabilities of an event should equal 1. If they don't, then something's wrong. Then you're missing something, or we would say it's not valid. Okay. Okay, so let's do some practice. So, you like Skittles, right? No? Skittles or M&Ms? Let's do Skittles. I'm feeling fruity this morning. Okay, so let's suppose a bag of Skittles has 60 pieces. Okay, and then I am going to, now I might forget colors, so I'm just going to give you some colors. This is the breakdown of colors. We're going to do orange, green, yellow, red, and purple. All right, let's put some distribution here. I'm going to say there's 18 orange, 13 green, 12 yellow, 9 red, 8 purple. Just, would you do a double check for me that adds up? Does that add up to 60? Okay, good. So, the possible outcomes then are getting an orange, getting a green, getting a yellow, and getting a red, and getting a purple. Okay, those would be the possible outcomes of one Skittle when one Skittle is drawn. And the number of things in the sample space is 60. Okay, and so when I'm doing my probability, I'm going to have all of them be out of 60s for one Skittle. Okay, so what's the probability I get? I pull in the bag and I pull out a green Skittle. Exactly, 13 out of 60. Let's talk about ways you can leave probability. You can leave it as a fraction, you can leave it as a decimal, or you can leave it as a percent. Those are the 3 valid ways. So unless I specify, I don't know, just do the most exact way. As a decimal, this is 0.216 repeating, it looks like, right? And as a percent, you would write that as 21.6 repeating percent. So just so you know, from now on, I'm going to leave mine as fractions because I have both of those things. All right, so then what if I said something like this? How about what's the probability that you pull in the bag and you don't like purple? You want to make sure, what's the probability I'm not going to get a purple Skittle? Yeah, so I am counting then all of the things but purple. Or you could just go backwards. Since there's 8 purple, how many things are not purple in the bag? 52 out of 60, which reduces to 13 out of 15 if I'm leaving it as a fraction. Okay, let's just do one more, just so you see how this works. How about the probability that you get red or yellow? You don't have a preference. You're still pulling one Skittle out of the bag, but what's the probability that it's red or yellow? So what would you do to figure out that? Add them together because we don't care if it's red or yellow. It's still one Skittle. So we have 9 plus 12, or 21 out of 60, which reduces to 7 out of 20.
Will we do like group that statements?
Will we do a what?
Like, they say red, then yellow.
Yes, that's what I'm going to do right now. Okay. When you do two or a multiple event, okay, there is something that happens. Now, I'm assuming that once I pull a Skittle out of the bag, that I'm not putting it back in, okay? So, but then this becomes kind of a multiplication counting principle thing. The probability of the one times the probability of the other, okay? So, let's say I said, I want to know what's the probability you get green, then another green. So now I'm pulling 2 Skittles out of the bag, okay? If you wanted to think of it in this way, we would use the idea of there's 13 green, right? So the probability that I get green on the first time is 13 out of 60. I'm going to assume then that green came out. Now how many Skittles are left in the bag? Only 59 left, and how many are green? 12. And so then I would multiply those probabilities together. If I was doing it as a fraction, I get 156 over 3,540, and you get 0.044. About, is that, let me look. Yeah, it's not exact, but we can do it as a fraction exactly. But another way to think of this is with a combination. Okay, so let's think of it as not one Skittle and then the second Skittle. What's the probability I'm going to grab 2 of them at the same time. It's going to be the same probability. So then on the bottom, I'm going to write this up here. I have 60 Skittles to choose from, and how many am I choosing? 2. So all of the ways that that could happen is 60C2. 60C2 would give me all of the ways that I could choose 2 Skittles of any type. So that's my total number of things that I'm counting. On the top, I only want to count the ways that I could choose green. So what's going, 2 green still, but out of how many? 13. So on the top would be 13C2. Do me a favor and calculate that with combinations and tell me what you notice. It's the same thing, right? Okay, so you can think of the, multiple events as combinations. Tomorrow we're going to talk about, because it's a little bit different, sometimes the probability is, it changes, not because you take it out, but based on what happens. Let me give you an example. Tomorrow I'll talk about, hey, if it's not raining, the probability you're going to play your baseball game is 95%. But if it is raining, the probability you're going to play your baseball game is 60%. So then we have to count different ways that happens, with rain and then without rain, and then there's a formula for calculating that. So for today, though, we would call these independent trials in the sense that the probability depends on the other because I'm taking one thing out, but it doesn't change, like the number of Skittles in the bag isn't changing or anything like that. All right, one last thing that we should review about probability are Venn diagrams. Did you do any Venn diagrams last year with probability? Okay, so let's draw a Venn diagram. Second, I think you guys have seen these before, right? They've got 2 overlapping circles. And just for, this is made up, okay? But we'll say that this is Comstock Park High School. So this represents all of the students at Comstock Park High School. And let me give you some percentages here. First of all, if it represents, I'm going to count playing sports.